Hi class, welcome to discussion on correlation and regression. We're going to get through most of this chapter today. Of course, like the other, if you have any questions, we're going to cover it again next week, Monday and Tuesday. So sit tight if anything seems confusing to you. Of course, like the other chapter, if you would have read it coming in, this will make a lot more sense to you. Otherwise, we'll just do our best to get through it. Alright, so far with hypothesis testing, we've looked at many tests that have basically been comparing groups, either one group to another, or in the case of ANOVA, we're looking at more than two groups. But everything has been comparing means. And the reason for this is because we're looking at causal type of questions. So we're not directly asking if an IV causes a DV, but that type of experimental condition lends itself to that question. So we are asking if the IV has an effect on the DV. So for that to happen, you have a certain level of manipulation, and then you measure the outcome of that manipulation. So your IV is always going to be something changed by the experimenter, and the DV is the response of that. And when that happens, it's a good condition in order to infer causation. However, we don't always have that luxury in psychological research. A lot of times we're just observing relationships as they naturally exist. So that lends itself to this chapter. The Pearson correlation is probably the most used and cited statistic in psychology. Why we wait until this chapter to introduce it is beyond me, but this is probably the most prevalent statistic that you will use, especially if you go beyond undergrad. So the reason why it's so commonly used in statistics is because it uses observed relationships instead of creating experiments where you are manipulating variables. Oftentimes, psychological research, you don't have that luxury to manipulate levels of anxiety to see what effect it has on depression. It's not really ethical to give people alcohol and see what kind of effect it has on your reaction time. Most of the time, we are just observing those relationships. We observe people in the bar and how much they drink, and then we observe their decisions behind the wheel. Well, that's a correlational relationship. We, as the experimenter, play no part in the manipulation of those individuals who engage in that amount of behavior. Rather, we are just documenting, where individuals are on one variable and where they are on another variable, and we're putting it all together to get a big picture at the relationship between the variables. So the purpose of a correlation is to see if two variables have a relationship. And the type of relationship we are most interested in the Pearson correlation, is a linear relationship. That means the two variables form a straight line, as opposed to a quadratic or curvilinear relationship where they form a curve. We can't really test that kind of relationship with the Pearson. So the linear relationship is simple. It's the shortest distance between 2 points. You draw a line from one point to another. However, when you plot all the points in your scatter plot, you can very easily get a pictorial view of the shape. Does it go in a linear trend, or does it curve and bend? So scatter plot is going to be your best friend for this chapter, because you can very easily see what the relationship between two variables looks like without having to do any calculations in the beginning. So we're not going to be using means or standard deviations in order to calculate this. We are going to be using variance again, but we're going to kind of change it up a little bit. So a linear relationship means that the definition means that as one variable increases, there's a consistent increase or decrease in the other variable. So if the other variable increases, remember that whole rise over run, and it's consistent, that's the slope. So that slope is consistent as each variable increases. So if the one variable increases and the other increases with it, then that's a positive relationship. If one variable increases and the other decreases, that's a negative relationship. I'll show you some examples of that. So we usually denote the sample population, the sample correlation with R, and the population rho. That's what that little cursive P is, rho, R-H-O. So before, when we had population mu, this is just the Greek letter for population when we're denoting a correlational coefficient for the population. We are actually only going to ever calculate R. Okay, that's our sample correlation. In order to calculate this correlation, we need data on two separate variables. So each individual is going to contribute 2 data points. This is not a repeated measures. Okay, it sounds like it at first glance, but it's not. They're going to contribute 2 separate data points on 2 different variables. So if you're looking at the relationship between anxiety and depression, each individual will have an anxiety score, that would be their X, and a depression score, that would be their Y. Okay, and like I said, there's no experimental manipulation. That's why correlation does not equal causation. And we usually use scatter plots to examine the data and especially test the assumption of linearity. We want to make sure that those variables form a linear relationship. So this is what a scatter plot would look like. This is the relationship between IQ, that's on my x-axis, and GPA, which is upside down, that's on my y-axis. And you can see they're kind of clustered around with the exception of a few very smart IQ people who have low GPA down here at the bottom. But aside from these guys, we have a pretty linear trend. They're kind of throwing off our line a little bit. But this is how you would examine a correlation first. You would plot your data points, each person getting an X score and a Y score. So after you do that, you can mathematically configure a number, a numerical response for what that correlation, what that relationship means. And if that correlation is a perfect linear relationship, 1 to 1, then it will have a correlation of 1. If it's a perfect negative relationship, it will have a correlation of -1. So correlations never exceed -1 or +1. They range from that value. Correlation of 0 means that there is no relationship. You cannot form a line. It's basically a horizontal line across because there's no relationship in the data. So generally speaking, studying statistics and happiness has what kind of relationship? Unless you're me, most likely it's a negative relationship. So the more you study statistics, the less happy you are. So as studying statistics increases, happiness decreases. Whenever you have an inverse relationship like that, that's a negative relationship. It could also be negative if you looked at it the other way. As happiness increases, studying statistics decreases. Okay, so it doesn't matter which one you're talking about, as long as it's an inverse relationship, it's a negative. Okay, when they're both increasing together, so studying statistics and happiness are both increasing, that's positive, or when they're both decreasing together. So studying statistics decreases and happiness decreases, that's also a positive relationship. Okay, we'll see more examples on that later. So +1 and -1 are perfect relationships, but that is near impossible to achieve. Okay, we have criteria to determine how strong a correlation must be in order to be significant or in order to be a strong relationship. Typically, you're not going to get a positive, perfect 1 or -1 relationship. Okay, so if they're close to 0, they're pretty weak. If they're closer to 1, they're pretty strong. So here's the same data again. This would be a moderate positive relationship. Okay, we don't have a numerical response for it right now, but it's pretty moderate. Here you can see that the relationship has gotten stronger. Okay, because those scores on the bottom have moved more in line, so we have more of a linear relationship that is positive. Here's a moderate negative relationship. You can see the inverse relationship between the two. Here's a perfect positive relationship. So this would be a correlation of 1, +1. And here's a perfect negative relationship. Okay, so this would be a perfect -1 correlation. All right, so let's talk for a few minutes about how to calculate the correlational coefficient. You can eyeball it, but we need to actually attach a number. So Pearson's R is constructed based on sums of squares. I know you're probably tired of hearing sums of squares, but I warned you about that at the beginning of the semester. So recall again the sums of squares formula. Okay, it's right here. Sums of squares, the definitional formula, is your sum of each x minus the mean squared. Or the computational is right below it, and that's x squared, sum them up, and the sum of your x's squared over n. So I want you to look at these formulas closely for a second. And even though this is the way we've always calculated them, think about that this x minus m squared, look at the formula to the right. Doesn't this make sense as well? That we could look at the same formula and just break down our x minus m. So x minus m times itself and then summed it up. This is the same formula, just presented another way. Same thing with the computational. We can separate this x squared and just say x times x, as well as the sum of x. We can multiply that times itself. And again, this is the same formula. So the formulas you're about to see for the calculation of R are derived from our sums of squares formula, but we're going to use these on the right. Okay? So they're going to seem scary at first, but I just want to understand that it's just a derivative of the formula that we've always been using. And that's because now we have two different variables. Up until now, we've only been interested in one x, one person's score. We haven't really been interested in more than one score. We haven't had a y. Now that we have a y, we have a new type of variability to introduce. Okay? So, what this looks like is, well, actually, let me go to, I'm going to jump to this formula real quick. This is our R formula. Our R formula says that we are looking for the correlation, the relationship between IQ and GPA. Those were the previous examples. And in order to calculate that relationship, we want to know how much the scores vary together and how much they vary separately. And by looking at those two things, we're able to see the relationship between the two. So, do they vary together more than they vary separately? If they vary separately more than they vary together, you're not going to have a very strong relationship. But if that sum of products, that numerator, if that is really high, that means that the two variables vary together a lot. As one increases, the other does the same or opposite. Okay, so that variability of them together indicates a relationship. So let's go back to the calculation of that. So the vary by itself, we want to see how much the x scores and the y scores vary individually. We're going to use the sum of the square deviations. It's basically the sum of squares. So we're going to subtract the mean from itself, multiply it. Okay, so x minus mean squared. This is the same thing that we've already done. The sum of products that we're going to introduce is what is different. So now we're going to take the deviation from each x and its mean and the deviation from each y and its mean. That's for the same person. And we're going to multiply them together. That's why it's called sum of products. So you multiply those two deviations for each individual, and then you sum them together. And you're going to get some experience doing this in just a second. So I want you now to go to your example sheet, and this walks you through what you're to do. So you take each individual that are here. Okay, you need to find, well, the mean is already given to you. You subtract the mean from each x, square it here, subtract the y from each mean, square it here, and you're going to multiply your deviations and sum them. And you're going to sum your sum of squares. Okay? And once you get your sum of squares for your x, your sum of squares for your y, and your sum of products for how much they vary together, then you can solve for your r. Okay, so go ahead and fill this out and find your sum of squares x, sum of squares y, and sum of products.